After completing those examples, you might have noticed a few patterns along the way. First is a plus x, or x plus a squared, is the same thing as x plus a times x plus a, which we can of course write like this. Because we're working with x squared values, we know that our binomial will always have a single x, because every quadratic expression we're working with today will just have a single x squared. You also might have noticed that your linear term is always 2 times a times x, because you're multiplying x times a and x times a, then adding the like terms together for 2 of those a times x terms. Finally, you might have noticed that your linear term is always a squared, because you're multiplying a times a each time. Remember that a could represent any number depending on what the constant is in your quadratic expression. In the next example, we're going to try working backwards by rewriting the standard form quadratic expressions as perfect squares. So I'm going to get rid of the bottom half of the table to make things a little bit clearer, and I'm going to put that rule back on the screen to help me. I know that based on my standard form expression, this value a squared is going to be equal to my constant term. Since I know that my constant term is 36, I can ask myself, what number squared equals 36? And of course, that number is 6. Let's try it out. X plus 6 squared. If this factored form were true, I would get x squared plus 2 times a times x. Now remember, we're trying out the value of 6 for a, so I would have 2 times 6 times x plus 6 squared. If I simplify that expression, I end up with x squared plus 2 times 6, which is 12x plus 36. And of course, that matches my original standard form, which means I've got my factored form right. X plus 6 times x plus 6. Now, if I wanted to check my work in another way, I could, of course, always factor my expression and simply multiply x times x equals x squared. X times 6 is 6x. X times 6 again, we're going to add another 6x. And of course, 6 times 6 for 36. Notice that we'll end up combining these like terms, 6x plus 6x, and of course, end up with 12x, which is the same exact process as above when instead we multiplied 2 times 6x. Let's take another example of x squared plus 8x plus 3. Earlier this unit, you learned something called the tabular method, which is a way of representing a quadratic expression in a chart. We're going to use this first, and I'll show it a second way in case you get confused. Essentially, we want to demonstrate why x squared plus 8x plus 3 is not a perfect square. It might be obvious to you by looking at the expression, but here's why. We know that we need to multiply 2 x's to get x squared. We also know that to end up with 8x, we're going to need to multiply 4 times x and 4 times x, so that we end up adding 4x plus 4x to get a total of 8x. Now, of course, if our binomial terms were 4 plus x times 4 plus x, we would end up with a constant term of 16 for an expression of x squared plus 8x plus 16. And that's not what we're looking for. We want to factor or create the factored form of the expression x squared plus 8x plus 3. Another way to think of it is by considering the way we usually convert our standard form to factored form. Again, we know that to get our linear term 8x, we would need x plus 4 times x plus 4, because of course we'd end up multiplying 4 times x and 4 times x to get 8x. Now, of course, again, we would end up with a linear term of 16, which is not the same as the standard form with which we started. However, we can get quite a ways by simply starting with x squared plus 8x and working to find a perfect square from there. Here, we do have a perfect square. It's not equivalent to our standard form, but x squared plus 8x plus 16 is equivalent to x plus 4 times x plus 4, or x plus 4 squared. So we can get creative. We're starting with x squared plus 8x plus 3. But if I add 13, I end up with a perfect square, x squared plus 8x plus 16. Of course, I can't just decide to add any term to my expression and expect it to be equivalent. However, if I add 13 and then take 13 away, this expression here is entirely equivalent to my expression x squared plus 8x plus 3, because of course 13 minus 13 is the same thing as really adding 0. However, if I add my 13 to 3, I end up with x squared plus 8x plus 16. So you can see that I simply combined 3 and 13, and I left minus 13 on its own. At this point, I can convert a large part of the equation, x squared plus 8x plus 16, into a perfect square, x plus 4 times x plus 4. And I'm left with x plus 4 squared minus 13. This expression is equivalent to our original standard form expression of x squared plus 8x plus 3, because I simply added and subtracted 13 in order to create this perfect square of x plus 4 squared. In a moment, when the video ends, I'm going to ask you to try the same exact process with questions 2, 3, and 4. I'll demonstrate question 1 to start. If I have the expression a squared minus 4a plus 15, I want to focus on the first two terms to create some form of a perfect square. I'll know that a minus some number times a minus some number will get me a standard form that at least includes a squared minus 4a. Now, of course, if I fill the blank with a 2, I know that a times a is a squared, and that I'll end up with two terms of negative 2a, because I will end up multiplying this negative 2 times a and this negative 2 times a. At this point, I can convert a minus 2 times a minus 2 to standard form, and I end up with a squared minus 4a plus 4. As you can see, this expression is a perfect square, However, the constant term plus 4 is not the same as our original expression, which was plus 15. So we'll need to get creative. Going back to my original expression where my constant term is plus 15, I can play around with that constant in order to simplify my expression and complete the square. If instead of writing plus 15, I write my expression as plus 4 plus 11, I have not changed anything about my original expression. I know that plus 4 plus 11 is exactly equal to plus 15. It's just written a little bit differently. However, now that I have a squared minus 4a plus 4 as a part of my expression, I can convert these terms into factored form. I end up with a minus 2 squared plus 11. This expression is exactly equivalent to our original expression of a squared minus 4a plus 15. Because remember, all I did was change plus 15 to plus 4 plus 11 and convert this component of the expression, my first three terms, into factored form. At this point, you have all the tools you need to complete the next few examples. I'm going to send you back to the original table where you should be able to easily complete the square without having to play with your coefficient too much, or your constant, excuse me. Then you'll move on to these exercises where you'll complete questions 2, 3, and 4. If you have questions, please ask by commenting on the original assignment or otherwise contacting me during office hours. Good luck, guys.